Hello, good afternoon. My name is Olugbengala from Matrices Tutors. Today we're looking at matrices. Matrices. Now, at the end of the lesson, students should be able to solve problems on matrices using basic operations, and also to be able to determine the inverse and determinant of 2 by 2 matrices. So we are looking at how students can solve problems on matrices using basic operations, which are addition, multiplication, and subtraction, and also determine the inverse and determinant of 2 by 2 matrix. What are matrices? Matrices are rectangular arrangements of elements or entries in rows and columns. Now, rows are horizontal arrangements, while columns are vertical arrangements. So, they are denoted by capital letters. That means that matrices are denoted by capital letters, while the elements are denoted by small letters. Also, we have different types of matrices. And matrices is the same plural, while matrix is the plural, or is the singular, sorry. Let's go on. We're looking at types of matrices, and we're starting with identity or unit matrix. This is the type of matrix which has its leading diagonal as what? As 1. It has its leading diagonal as 1. The example below is a 3 by 3 identity matrix, and the order of the matrix is what? Is 3. The order of the matrix is 3. Let's go on. If you look at this matrix, it is 3 by 3 because it has 3 rows. So this is row 1, row 2, and row 3, horizontal. Then when we look at the vertical, this is column 1, column 2, and column 3. So this is a 3 by 3 matrix. So it is what? Identity matrix, because the leading diagonal, you can see 1, 1, 1 here. This is a diagonal. It has 1, 1, 1 on the leading diagonal, and every other element equals to 0. So it's an identity element. The second type is what we call the null matrix. This type of matrix has zeros as its entries. So the example below is a 3 by 3 null or empty matrix. You can see all the elements are what? 3 are zeros. So we call it null matrix. Then square matrix now. For square matrix, this type of matrix has equal number of rows and columns. So we have 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so on. The example here shows that these ones are square matrix. This is a 3 by 3 matrix, and this is a 2 by 2 matrix, which is a square matrix. Then we move on to rectangular matrix. This type of matrix does not have the same number of rows and columns. For example, 2 by 3, 4 by 6, 3 by 7. So they do not have the same number of rows and columns. So they are called rectangular matrix. And the order of this matrix is 2 by 3. You can see how many rows we have here. This is row 1. This is row 2. And how many columns? Column 1, column 2, column 3. So row first, then column. So we have 2 by 3 matrix. Let's go on. We also have what we call the row matrix. This is a matrix having only one row of elements. You can see from here, it's only one what? One row. So it's a row matrix. It can have as many columns as possible, but only one row makes it a row matrix. Then column matrix is a matrix having only one column of elements, one column, just one column. It can have as many rows as possible, but just one column. Then we move on to basic operations on matrices. So let's look at addition and subtraction. 2 or more matrices can be added together or subtracted from each other if they have the same number of rows and columns. If they have the same number of rows and columns. So they are called similar matrices. Looking at an example here, this is matrix A, matrix B. So we can add these two matrices together because matrix A is a 2 by 2 matrix. Matrix B is also 2 by 2 matrix. So we can add them together. And how do we add together? We say 2 plus 5 which is what you have here. The next one will be 4 plus 7, which is what you have here. Then we have 3 plus 4. Then we have 5 plus 3. And by the time you add up this, you get 7, 11, 7, 8. So this is the addition of the two matrices, A and B. Likewise, you can also subtract because they have the same order. So you also subtract correspondingly. 2 minus 5, 4 minus 7, 3 minus 4, and 5 minus 3. And so you have minus 3, minus 1, and 2. Let's go on. Multiplication of matrices. Two or more matrices are conformable for multiplication if the number of rows in the first matrix is the same as the number of columns in the second matrix. This is second matrix. So what do we mean by this? If you look at matrix A is 2 by 2 and the number of rows here is 2, then matrix B, the number of columns is 2. So that means we can do what? We can multiply them together. And when you look at it from here, how do you multiply? You pick the first row to multiply the first column. And that will be 2 times 5 plus 4 times 4, which is what you have there. Then after that, you move on to the second column with the first row here. So it will be 2 times 7 plus 4 times 3, which is what you have here. Having done with the first row, then we move on to the second row of the first matrix. It will be 3 times 5 plus 5 times 4. The other one will be 3 times 7 plus 5 times 3. And by the time you sum up everything, we're going to have 26, 26, 35, 36. Hope that is clear. Let's move on. Let's go to the determinant of a 2 by 2 matrix. Now, the determinant of a 2 by 2 matrix can be calculated by subtracting the product of the lagging diagonal from the product of the leading diagonal. What do I mean by this? Let's look at an example. Find the determinant of matrix A equals to 4, 6, 3, and 7. Which one is the leading diagonal? It is 4 and 7. So product of 4 and 7 is 28. Product of 6 and 3 is 18. So 28 minus 18 will give you 10. And so that's the determinant of matrix A. Then we have to note this, that when the determinant of a matrix is equal to 0, then that matrix is a what? Is a singular matrix. But if the determinant of a matrix is not equal to 0, then we call such matrix a what? A non-singular matrix. In our previous example here, the determinant here is equal to 10. It's not equal to 0. So this matrix A is a non-singular matrix. I repeat, is a non-singular matrix. Let's go on to the last slide. Here we are looking at inverse of a 2 by 2 matrix. Now, for you to be able to find the inverse of a 2 by 2 matrix, you need to find the determinant of that matrix first. But then, if you multiply a matrix by its inverse, you must get an identity matrix. What do I mean by identity matrix? Identity matrix for 2 by 2 is 1, 0, 0, 1. But for 3 by 3, you have 1, 0, 0, 0, 1, 0, 0, 0, 1. This is for 3 by 3 matrix. So we call it identity matrix I for 3 by 3. And this identity matrix I for 2 by 2. So let's go on. Example 2 says we should find the inverse of the matrix B, which is 7, 4, 6, 3. So the first thing is to find the determinant, which is 7 times 3 minus 4 times 6. And that will give us minus 3. So to now find the inverse of B, it will be 1 over that determinant, and determinant is minus 3. Then what you now need to do here for this matrix is to interchange the leading diagonal. So 3 comes over here and 7 comes here. So it becomes 3 and 7 here. Interchange. Then the lagging diagonal, which is 4 and 6, you multiply this 4 by minus 1, it will give you minus 4. 6 times minus 1 will give you minus 6. Then it will now be 1 over minus 3 times 3, which will give us minus 1. Then 1 over minus 3 times minus 4 will give us 4 over 3. 1 over minus 3 times minus 6 will give 2. And 1 over minus 3 times 7 will give us minus 7 over 3. And so this is the inverse of what? Of a 2 by 2 matrix. So we are ending everything here. I want to believe it is clear. And if there are questions, you can get across to us on our YouTube channel. Thank you and bye-bye.